Well, it's 1:40. Let's start. Are we on? Yes, we are. So hello, everyone. Thanks for having me here at NDC Oslo. I'm very happy to be here. My name is Karel Zikmund. I work on .NET team, and I'm going to tell you something about war stories from .NET team, where I have been for the last 14 years. And a little disclaimer before we start. I rehearsed the talk this morning and found out that there's too much content, so I removed some. And then I did Twitter poll. If you want advice, what do? You go to Twitter, right? And Twitter poll told me like, yep, it's better to kind of pace through. So I apologize for some of those stories that I'm going to talk about. I'm going to probably be a little bit faster. So just heads up. And what I'm going to talk about. I'm going to talk about stories. So stories from that I mostly lived through, either directly as a developer or maybe as a manager that has happened on my team. Some of the stories are actually not that I directly was involved, but it's something from the team, and stories that I kind of think are cool. Mostly those are some investigations on .NET team, runtime, base class library, something like that, and they're not just from me. And hopefully I'm going to show you as well, or that's the key, some kind of lessons that we have learned along the way from some of these cool or interesting, at least, investigations. So what's not on the agenda? You won't see any source code. You won't see any debugger. There is one call stack, and that's it. So if you expect debugger and source code, this is the wrong talk. Please leave, or don't get disappointed, something like that. And you don't need any deep knowledge of .NET. I'm going to explain some of the concepts, but if you miss them, that's fine. If you are into debugging and advanced debugging techniques, this is the talk you should have been to yesterday. So those are crypto guys, Kevin and Christoph, and they did awesome job with WinDBG. No such stuff over here. I'm going to start with my first story. So my first serious investigation on .NET team happened actually quite early. So it was 2006. I joined 2005 in October. So I was 3 months in. And this investigation kind of comes in, which was pretty fun. So it was some kind of build lab team in Windows, some component. And they're building their product. And to set the expectation, so to set the context, I was as I joined, I was owner of Metadata component, part of the CLR for the runtime. So they have this, this build lab, dozens of machines, crunching builds every night, probably multiple times a day. And what happens, like roughly once per week, they get a build break. And the build break is actually access violation dialog. Back then, nothing dismissed it, so they had to log in on the machine, click the OK, and restart the build. Kind of like bummer on productivity. And so they started investigating. They went through like, oh, it must be MS build problem. So they involved MS build people. MS build people said like, OK, take out the C# compiler, or repro or the command line. Try that. OK, that's in C#. Let's move it to C# compiler. C# compiler look at that, and they said like, yep, that's somewhere in metadata. So boom, Karel, you go. That was actually the investigation. Before that happened, what was funny that they noticed that, hey, we actually updated toolset of the CLR, of the compiler, just a few weeks ago. That must be it. Like, we updated to 2.0 RTM, suddenly it started failing. You're it. It's your problem. That was interesting attitude. And, they were kind of right, as you will see. So the good news is that these people, well, they're smart, they're good, and they tried to create a repro for us, which is, lifesaver. So first they tried it and kind of in a loop, building the same stuff over and over again. It failed roughly once in 50 runs, which is great. And then they ran it overnight, and you see some numbers: 77,000 iterations over, not overnight, actually it was over weekend, I believe, or overnight, I don't remember. 247 crashes. So some significant reproducible thing. So good, we have a repro. And out of the repros, we actually got call stack. Before I show you the call stack, there was some funny quotes actually in the old emails I found out. So the first one basically said that, hey, it looks like from the call stack that some boilerplate stack checking code is wrong. Now, I wasn't experienced enough, 3 months in the job, right? If I saw it today, the first thing would be like, alarm, alarm. This is a security issue. As soon as you mess up with stack, something is wrong and it's gonna bite you. Anyway, back then nobody noticed that, so we went on. And other funny, comment, that was in the email, which basically, the person from C# team kind of pinged me on IM, like, what do we do? And I basically said back, like, yeah, this is great. but I'm new to the code, so you gotta help me. You have to, it may take some time. So they set it as well to set the expectation with Build Lab. It was, pretty funny thing. Anyway, we got the call stack. This is the call stack. I removed lines, things, so make it a little bit more readable. At the bottom, you see the C# compiler. Higher up, you see kind of the as well C# compiler, which is kind of like emitting metadata. And at the top of the call stack, it's us. And over there's some kind of read-write log, which suddenly blows up, and AV. So obviously, that was not enough. Luckily, we got like heap dumps, so we could look at the assembly code. So that was a great 3 days of learning how to use my latent knowledge of x86 assembly and figure out, like, what's the locals, what are the parameters, how it flows, and debugging through that. It was lots of fun and great learning opportunity. If you want to learn assembly, I recommend some issue like that, like really, really useful. So first thing on that, when you get call stack like that, you get heap dumps. So it's like, who corrupts the stack? And because we are in the world of managed code, like GC, and nope. And why not? Because this is C# compiler. Remember, this is before Roslyn even existed or was a thing. So it was all native. So GC doesn't even run, right? That the parts of the metadata emitter or metadata reader was actually, it was the native part of the code, and no GC ever run. So no, GC wasn't it. When I dug deeper, I found that actually there was one call, on the call stack, higher up on the call stack, as you've seen, that suddenly kind of some data changed. Like, on one hand, it was like, I'll make it up 5, and if you looked farther down, it was 4. Turns out that it was actually a single bit change. And you look at that and say, like, who corrupts, just one single bit? What could it be? Could it be like GC card table like updates? Those are the kind of weird things that set up things. And then like, no, we already said there's no GC in that process. So it was actually a good experience of like myself and as well others first jumping to conclusions to the known patterns and then realizing like, yeah, they are not quite applicable when you think that they should be. So GC it is not it. So what else could it be? Could it be like hardware flaky? Like that sounds stupid, right? Why would it be always on the call stack? But maybe yes. Turns out that it was actually a hardware issue. How I found out, I asked actually the team, like, so guys, by any chance doesn't reproduce only on one machine? And the answer was like, how did you know? Well, I had a hunch. And then comes the next question. So long story short, probably memory or CPU, whatever. But then, kind of you think about it and say, like, so why does it fail always on the same call stack? That just doesn't make sense. Once per week, right? Or once per iteration. The iterations once per 50. You know what? I don't have good. It's a good question. Why? I have no good answer. Some magic. They took the machine out. Everything worked since then. So that was my first investigation on the runtime team, which I found funny and interesting, and which actually taught me some things. And the lesson that I learned mostly from that is that debugging hardware errors is actually costly and hard. And the key takeaway is that taught me to ask always one question for anything which looks fishy, weird, and stuff, and that's, does it repro only on one machine? If the answer is, oh, we didn't try it on more machines, like, OK, stop talking to you. You try it on another machine. When you see it on 2 machines, then we can start talking. So now I come over as smart, and everything. It's not as Dutch. It took me actually one more hardware bug to kind of debug and waste like 1 week or something. And then I finally learned this lesson. And honestly, since then, that's the first thing I ask. Interestingly, over my career, actually, I ran into one issue, which I don't remember exactly, which was somewhat similar. It was actually not a hardware issue, but it was some driver issue. So the symptoms were that you got this weird thing happening, but only on certain machines, which had the same, I think, graphics card or something with the same driver. Solution to that, like, sometimes you might want to ask, or I might want to ask, like, hey, can you try different hardware, just in case, that you can really reproduce it. And actually, there's one even extreme version of this. If you know Maoni Stephens, she's our GC guru for years. Like she's the awesome GC. When I talked with her about this story and like how cool it is, she's like, look at me and like, yeah, you know what? I don't even trust VMs. This was like back, let's say, 10 years ago. Whenever someone comes like, hey, this is GC bug, first thing I'm asking them like, does it reproduce on real hardware? If you don't have the answer, I'm not even talking to you. Well, obviously, sometimes we are, right? When there's business enough reason, we do. But it was funny that the perspectives are very different. And it was during the time when kind of VMs had like still kind of problems in their drivers and things could get corrupted on behalf of your process. And chasing down GC issues is extremely difficult. So that's how she shielded herself from that, at least for a while. Probably she doesn't do it these days because everything is VM. And ask for people to try to reproduce it on real hardware. Anyway, so that's my first story. And because I started in metadata, owning the metadata component, I'm going to continue with another metadata story. For that, I'm going to first introduce some kind of background on metadata format. We will need it. So metadata in a nutshell is basically describing your program. If you're not .NET developer, so hopefully you are, DLL or XZ, when you have that, there are two parts. There's the code, the IL, which is for Java words is like basically the bytecode, and there's the metadata, which describes types, who inherits from what, like which method starts at which offset, and those type of things. The metadata is basically just the database. I think it was invented by 4 people who kind of came from database background, so they used the first thing that they knew, and it's a fitting format, actually. It has rows, it has columns, it has tables. Example is table of type defs, which are definitions of types. In the table, you have kind of rows, kind of entry for each type. And each column is something like, for example, flags, or you have there information about like type name, namespace, what it extends, or method list. And we're going to get to that. That's the important part. When you have references between these tables, they are not, for example, the strings are not exactly directly in the table. The strings are on so-called string heap, so on a side, and you have only index into that. Now, the trick is because back then, when it was designed like 20 plus years ago, I believe, back then, like, memory or size was very important. So there's some kind of primitive compression basically saying like, oh, if you're indexing something which is less than 64K, you can use only 2 bytes. Now, if it's more, like, okay, you got to use 4 bytes. So basically, statically per each DLL or XZ, when you look at that, it has information like how many strings do I have, how many methods I have, how many types do I have, and based on that, those indexes are for specific references, either 2 bytes or 4 bytes. So what can go wrong with that? All right, sorry, skip too far. So I need to invest first in, want to explain what the method list means here. So each type has some methods, usually. And the method list is a smart way how to basically saying like, hey, here's my first method. And there's a list, and it goes on either until end of the table or until the next type method list starts. So in this example, we have method list, method number 10 on type foo, and type bar starts at method 11, which means that the type foo has only one method, and that's going to be the method number 10 at index 10. Hopefully clear. So what happens if the last type def, let's say the type bar in this case, doesn't have any methods? What do? If you look at the spec, I'm going to show it even later, you're basically supposed to kind of point it to the +1, so the next one that doesn't exist. So when you look up the method list, you go to the index of method, you see, oh, this is the one that doesn't exist because I have only, let's say, 20 entries. This is pointing at 21. OK, I'm done. No entries. All right, that makes sense. This is the definition. So method list will be max +1. But what happens if you have exactly 64K minus 1 methods? That's not going to end up well. Because if you add 1 to that, what's going to happen? You overflow. And I said before, like each time you decide, or at the, by sizes and everything, do I use 2 bytes for representation or 4 bytes? Because I have FFFF methods, how many bytes it is? It's 2 bytes. But now I'm supposed to index something if the last type is empty, which is actually requires 4 bytes. So what do you do with that? So first of all, let's look at the CLI spec, which exactly describes what it is, just like for reference. And basically, it explains what I just said. Like, if you have less than, not less than equal or equal, but less than 2 to 16 rows, then you use 2 bytes, otherwise 4 bytes. And by the way, the method list is from 1, because 0, even though we're developers and we love 0-based, 0 is null, so that's forbidden. So 1, 2, row count plus 1. And that's basically, when you look at that, the problem that we discovered is that in certain cases, if those two things collide, you have bug in the specification. How do you fix that? Well, you don't. That's the kind of narrative, because fixing this bug means going change the specification, going chase down and all the ecosystem, all the profilers, debuggers, Visual Studio, ILSpy, Reflector, whatnot, and go and beg them, guys, can you please change? Can you please make this special case that if it's this, then do something else, right? That's a lot of work across the ecosystem. So it's extremely expensive. And to take some perspective, actually, Michal, who kind of investigated this, because by the way, I forgot to say that this is a story from, I think, this February or last February, so quite recent. He said it nicely, like, given that this happens like once in 17 years, maybe we don't have to fix that. And it was actually the WinRT team. They produced some WinMD files, and they just happened to run in case that they had the last type, which was exactly as the FFFF, and exactly the same number of methods, ran into that, and the type was empty, or didn't have any methods. It had maybe properties or fields. So the other thing that you can start thinking about is like, how do you compensate for such a bug? So we ran through a couple of interesting things. First of all, you can start playing games and rearranging order of types. As soon as the last one is not the empty one, you're good. Well, how would you like it if your compiler sometimes changed order of your types as you define them, from the deterministic way? That's usually kind of like not good. So that's kind of nasty thing. We kind of punted that. Their option actually was that to emit a fake type at the end. If we detect this situation, exactly this kind of overflow, one-off thing, let's emit one fake type. Again, how would you feel if your compiler here and there sometimes randomly injects new types, and then you start reflecting over that, and then you say like, what the heck is this, right? So again, not a good thing. The only reasonable thing that we thought for is like, if it's overflow, you know what? Let's use the 0. Let's let it overflow. Let's use the 0. But suddenly you have to tell everyone, all the the ecosystem products, like, folks, yeah, you gotta deal with that special. Like, it's not as obvious as you seem. And that's where we decided, you know what? It's not worth to fix every single bug, especially if it's high frequency, like once per 17 years. Yeah. So we decided to punt it. It's still actually open, just in case one day we might maybe fix it, but I don't think so. Well, we're gonna wait another 17 years. If we have one more hit, maybe then. Alrighty, that introduces us into something, or this type of fix would be basically a breaking change. Breaking change to many tools, many existing kind of metadata readers and things. Breaking changes are interesting topic on its own. So I would like to focus on that. First observation is that everyone, and I mean everyone in this room, everywhere, when you hit a bug, especially in runtime or Windows, the first thing that you're gonna say, like, I want it fixed. It's a bug. Everyone does that. It's natural, right? We're developers. You find something somewhere, you're really proud, like, yeah, I found a bug, go fix it. Well, turns out nobody likes to be broken as well. And those two things kind of don't work well together. Because what we observed over time, and this is kind of quote from one of our architects, not super hard data, but roughly in 10%, 1 in 10 changes is gonna introduce some unintended consequences. No matter how many code reviews, how smart people, doesn't matter. 1 in 10 is gonna have something unexpected. Now the question is it gonna be side effect that is okay and minimal and nobody cares, nobody hits that, or is it something that's gonna do boom? And those two things, as I said, like everyone wants their bug fixed, but nobody wants to be broken. That's where we, especially kind of in the platforms, have to be extremely careful to which bugs we choose. Sorry, which bugs we fix. We have to choose. We have to be kind of conscious of all the potential consequences. Obviously, the people in the first category. So if you find a bug, like often I see on GitHub and everywhere, people asking like, "But it's a bug. Like just fix it." Like, no, it's not as simple. And over my career, I actually ran into one extreme case, and that was actually that a perf improvement broke customer. You would say, like, would think that, I improved perf, good, right? And what happened, I think it was something around type loading or whatnot. We made some optimization, and turns out that there was one customer, something important that came back to us, that actually was relying unintentionally, obviously, on this slow speed because they relied on the order how things are initialized. They should not, but there's a reality, right? So they relied on it. And when we make things faster, they got broken because things got initialized in different order. They read something before it was initialized, so it was 0. Boom, their application stopped working. Obviously, it was some kind of like in-place update of .NET framework, so it was probably not them suffering. It was their customers, and they were unhappy, to put it probably mildly. What do you do in such situations? If you take this to extreme, you should not change anything, which kind of sucks, right? That doesn't make sense. So in that case, I believe that we just said the right thing. Like, yep, sorry, you basically had a bug. I know, it's not your fault that it's your fault kind of that you depended on something that is kind of not guaranteed. But we understand. But you gotta change. There's nothing. We're not gonna back out perf improvements just because you had this dependency on this. And the key lesson from these kind of things I have learned over time is that basically everything has a risk of breaking someone, if it comes down to making perf improvement. And I have a couple of more fun stories on the breaking changes. One is very interesting, last build. So it was end of Windows 8 on ARM, and I think it was the first Surface RT release or something like that. And one of the last builds, we found out suddenly started. What happened is that suddenly finance application started crashing, and obviously Microsoft, Surface RT was a big thing back then. So application on the first start fails. The application team was not happy, to put it mildly, and eventually they came to us when they kind of couldn't figure it out. It turned out that there was actually a latent bug that was there for months. It was there actually since beta time. And it was interesting to find out what triggered triggered this bug. And there was two conditions. First one was that there had to be method in engine images. If you don't know what it is, ignore it. Serialized on the disk, AOT, ahead of time compilation. And it had to be exactly, if it was on the boundary of 8 kilobyte pages, that was one condition. The other condition, that GC had to be triggered twice while this was on the call stack, which means that the application had to be under some stress. Starting application, that can happen, right? Application starts, lots of things happen, on multiple threads. It happened in finance, and it was actually some kind of networking part, and that we found out that actually some totally unrelated change somewhere just was lucky enough to push this method of default proxy, which took enough time that under stress was twice during GC on the call stack and was unlucky to be on the border of the 8 kilobyte pages, and big bada boom, you broke finance application. And the change, I don't know what it was, we didn't track it down, but basically the outcome of that is no matter what change, if you say like, oh, this is the safest change, I look here, like, look, like I can prove you that this is right. You don't know what it's gonna cause farther down the line. Obviously, we should not be that paranoid, even though sometimes we should. But the key takeaway from that is like anything, and I mean literally anything, has a risk of breaking. Even like I've heard stories, I didn't live it through myself, even just triggering rebuild. Even that can suddenly kick off, some latent bugs and stuff. There has been stories about that. I don't have them personally. So again, should you be so scared not to do anything? Probably not, but those are some of the things that sometimes you have to consider. And when you see and hear on GitHub or somewhere from us, like, oh, we're not gonna fix this because it's risk, and you look at that, it's simple, just like look at the code, just fix it, right? I can prove it to you that is right. Like these kind of stories and experiences come from the other side to our minds, and that's why sometimes we say politely, sorry, yeah, like no, we're not gonna fix it, even though it's super simple. Of course, only if it's end of the release. The other kind of angle of the breaking changes and stuff, or fun part, is actually that they may have like really huge impact. And this is a story that actually I didn't live through directly, but it kind of is very well known on our team as a poster child of like, you shall not change things at certain time. And it was actually patched to .NET framework, so boom, blast on all the 2 billion machines or whatever it is. And certain text software, which I'm not gonna name, broke. Okay. The trouble was that the part that broke was printing the text forms. Okay, not good. Well, the update was pushed right before the text deadline in the US. And when you put those two things together, it's like, oh my gosh, that's not good. It wasn't good. Customers were unhappy. It was not just the text software, it was their customers who they kind of like start printing, one day before deadline or a few hours. I don't know how you do taxes. In Europe, oftentimes the employer does it for you. I do them last minute. I'm a procrastinator. I hate them. Many people do. And guess what? I do them online, but back then people probably, sometimes print them. And they cannot print their taxes. That's bad. That's bad. What was funny, you can look at it like, oh, you maybe didn't test enough. Turns out, we did test that. The text software company tested that scenario, except we printed everything into PDFs. We never used the printer, because why would your test pass always print out something on the printer? The bug was so specific that it broke only printing on the printer. Yep, tough luck. So what's the lesson learned from that? Around certain dates, be careful. For example, tax season, and there might be other parts. For example, even end of the year. And this is old story. This is probably 10 years old or something like that. But you see similar things as well in, for example, online shopping. Companies, right? They usually, before their season, like Christmas is their time, and they kind of have most sells maybe 50% or 30% of their all volume. They basically stop pushing anything into production, just to avoid any risk of anything breaking. So I have friends in those companies, and they always like, yep, I cannot do anything until January, lockdown season, which starts in November. So it's very similar. What's interesting on this, that you see certain similar patterns even in frameworks or operating systems, which is not quite super intuitive at first sight. But yep, we had interesting experience. Alrighty, and now I'm gonna go through the fun part, networking issue. This is last story. It's a little bit longer one. It's very dear to me because I lived through that last July. It was lots of fun. And because we already pushed out the security fixes in last August or something, I can hopefully talk about that. And it was very interesting and eye-opening. So the story starts not more than in July last year, but it starts actually December before, which is 2017. And in January, there was some kind of researcher running some ML workloads, mining thing, inside Microsoft, and on models, and he used Cosmos. I'm not sure, is Cosmos now public? I think it is, right? Yeah. So like processing lots of data, large jobs and things. And here and there, he got weird results. And eventually, they got through Cosmos and some kind of couple of SDKs to us, and told us like, this is weird. Like he's getting like weird responses for these requests. So what's the first response to that? Being trained of like, how people ask us for various weird things that have nothing to do with us. First thing is like, are you sure it's on the client? Well, our team back then, or my team now, owns actually networking client side. Are you sure it's on the client? It's not on the server, because if we're chasing down the server, if we're good collecting logs from the client, it's not gonna help us, right? We need to find out where the problem is, where it starts. So they started doing some kind of logging. I think that they deployed Wireshark because in production, in Cosmos, that's not fun, so they had to know lots of people. And eventually we proved, or the Wireshark traces and other traces proved that actually it's, server is fine. It gets the requests, it sends the right responses, so something is fishy on the client. So at that moment we were like, okay, yeah, we might be involved. So it's either us as a networking side or something underneath us, which is like OS networking. But, when you're on top of the stack to blame, guess what? You got to investigate. So we started investigation, and it was already kind of, I think, February. And so we sent them, actually, we were suspicious about, we look at the code around, what could happen. And it was like, some kind of weird buffers. So it's like, yeah, no, that's weird. We gave them actually some logging first. They collected logs. They were useless, obviously. We didn't encounter something like this. So we created private builds for them with, special logging points, gave them the private builds, and then waited. Turns out that, after months, we pinged them, so what's up? Do you have the logs for us that we can take a look at that? And it's like, no, it's gone. The repro is gone. Like, what do you mean gone? Yeah, we updated to different cluster, whatnot, different hardware, and doesn't reproduce anymore. And even back then, the reproduction was once per week. The researcher kind of got wrong results. So I don't know how many kind of data points he cracked in, but it was not quite quite that. So with that, if you don't have repro, even though if you suspect something was really fishy, and well, actually back then we didn't know if it's just one machine. I didn't even get to ask that question, I believe, or maybe I did, and they told me that probably multiple. But we were suspicious. We probably knew that there's something fishy, but you have no leads basically. You have nothing to do. So we kind of put it to ice, and then in May, so 2 months later, kind of similar report comes, and it was an email, and it was interesting that it was one email and lots of people and hey, we see some weird things, we send requests, and something wrong comes back. What the heck? It might be networking team. And when I looked at that, we actually we started looking at that, and roughly, slowly, first okay, guys, did you check server? Did you check client? And in 2 weeks, suddenly it blew up because there was multiple teams. It was suddenly 5 or 6 teams. Back then, I actually realized suddenly that the email in May actually it had 2 teams on the email. They somehow found each other. They have the same problem and came to us together. And I was not able to kind of decompose that information out of the email. It was, was funny, kind of. And then we had roughly five teams kind of knocking on our door, hey, something fishy is happening. So it was suddenly all hands on deck situation because when I'm gonna I think get to that later, but basically when you provide different response to requests or something like that, that might have some serious consequences. We're gonna get to that. Luckily, this team or the 2 teams had awesome thing. They worked on a repro. That's please, and whenever you can work on small repros, as small as possible. So they had very simple thing, and in 20 minutes it was able to reproduce the program. Then they kind of tweaked some parameters, whatnot, and in 1 minute you had a repro, which is awesome. It's amazing. Makes life so much easier. And on top of that, even the best thing ever, they were able to reproduce it under time travel debugging. If you don't know what time travel debugging is, it used to be called IDNA and TTT or slightly different technology similar. Go find out. It's only in WinDBG, sorry, but it's a lifesaver. Basically, naively, you can think about it that the whole execution of the program or part of it is recorded instruction by instruction on each thread. The trouble is that the recording has 8x or 10x overhead on the application. So oftentimes, if you can reproduce something, you run it under TTD, suddenly it doesn't reproduce because different timing and things. But as soon as you catch it under TTD, you're golden. You're done. It's just a matter of time before you get to that. The beautiful on the recording is that actually you are at the time where the error happened. You can set breakpoints, data breakpoints on read or write, or breakpoints on methods, and you just say, go back, and it reverts back the kind of execution time and say, oops, over here, it was triggered. So when, for example, if you remember the hardware bug, the bit flip, right, that wouldn't probably show up, but if there would be really GC or something flipping your bit, you would just set, hey, I have this data, this bit shouldn't be set, tell me who wrote it or who wrote into this thing. You could just go back in the trace, which is just lifesaver. So with that, we were able to kind of root cause the issue into something that was actually HTTP pipelining under stress. The funny part was that it was a 13-year-old bug, which out of the blue started kind of reproducing and messing up with our stuff. If you don't know what HTTP pipelining is, I'm gonna do a quick intro on that. So classic HTTP is that you have a request, you send it to the server sends back what? Response. Simple, right? Now, if you imagine you do it over and over, you have several connections. You usually don't have too many. Default is 2, I believe, in .NET Framework. Sorry for that. But if you have like maybe 100 or something, you have basically limited pipeline or limited kind of what is it called? Limited way how to communicate with the server. If you want to reuse the same connection for another request, you had to wait for the request, which is kind of time to server and back, which takes time, so it's kind of slow. So HTTP pipelining introduced the thing that you can actually, on the connection, you can send multiple requests even if you don't get the response yet, and the server has to send the responses in that order. Simple, right? You just kind of avoid the blocking on getting the response back. You pipeline things. Kind of IS64. Awful thing. Anyway, when you get, what happens if you send, for example, request 1, then request 2, before you get answer, then you get response 1, and later on you get response 2. Life is beautiful, it's associated to the right things. So what was this bug about? The bug was about if you had at least 3 requests pipelined on a connection. And when cancellation of requests was involved, timeouts. So that was the stress part. The system was so stressed, so overloaded that here and there something was canceled. Now, if you cancel the first request, what do? What our code did? It did the right thing. It looked at the at the connection and said like, well, the first response that comes back is gonna be to the request I don't care about anymore. So, boom, throw away the connection. Life is beautiful. Now, what if you would do it with request number 3 in the last one? The code, what it says, like kind of natural, like said, like look at it and it's like, yep, just like listen to the first 2, throw away this one and mark the connection. Once you're done with processing request, just close it. Don't queue more. Again, simple. You would get response 1, you would get response 2 afterwards, and then you would just close the connection. Now the trick comes, what if you cancel the request in the middle? Obviously you can come up with, right now from top of head with the right thing, probably what should happen, but what the code actually does, it removed the request from the queue. Looks kind of innocent and kind of similar to what the request 3 did. Except that you get that response 1, good, they're associated with request 2, and then you get response 2, except the response 2 is associated with the request 3. Boom. So in certain load situations, we associate the wrong response with the request. And that can have multiple side effects, as I said. For example, imagine the request was something, I'm not going to name it, the product's affected, but hey, does this data exist? And the answer should be no, but you get different response which says, yes, go on. You just lost data because you got wrong information. Imagine that it's actually in, that was the worst case, it was some multi-tenant server, something large that has multiple customers. And the request 3 was like, give me data about customer X. And the response 2 was, hey, here's data about customer Y. That's not fun. It's kind of mixing data. And if you're mixing customer data, nobody wants that. So that happened. That was also fun. We had workaround for that. Just disable pipelining. Luckily, it was present there. It had some perf impact because, as I said, the pipelining was invented so to kind of streamline and get more throughput. But hey, if you have to choose between security, potentially be broken, and being a little bit slower, what do you choose? I choose slower, or everyone sane does, right? So that's what they did, which is cool. And in parallel, we worked on a fix, and we were verifying the fix. And repro, after 4 hours, failed again with our fix. And we were like, what the heck is going on? So you come back, and it was exactly the same symptoms. You send something, you get the wrong result. And we just fixed that. And we were quite sure, like, well, sure. it was code archaeology. It was ancient code. I had to learn it actually for the first time. Our expert was just on vacation, by a chance. That happens. And but anyway, we kind of looped in a couple of experts who used to work around that code base, and everyone was like, yeah, that sounds right, when you explain it this way. So we were digging. What didn't help is that the repro that we had was extremely sensitive, actually, to workload in the cloud, on the network. So it was in July. My family was already in Europe, so I worked overtime because this was fun part, and it needed to get done. And I couldn't repro it in the evenings. I was like, what the heck is going on? Then actually later we found out that actually between 8 and 17, the load was exactly right. It got the right stress, and these things reproduced. If you did it after hours, boom, your repro is gone. So that didn't help with debugging, by the way. So we tried, again, time travel debugging because it's lifesaver. Tough luck. We were not lucky to catch it under time travel debugging. So that didn't help us. And we got, again, suspicious, we remembered our suspicion from January, so this is July, half a year earlier, about the buffers. So we said, like, oh, we have this kind of special logging. Let's try that. And of course, we discovered that there was like bad buffer lifetime management on the sending side, actually. So when we were sending a request, before it went out, we reused the buffer for another request, and the other request wrote the data into the payload, and then this request sent it out. So what ended up, actually, the request for one server from the other one got sent to another server, which was fun. That's actually how we first found out and about it as well from production in parallel. It turned out that this bug was 5 years old in the code base since .NET 4.5.2. Interestingly, it was introduced at the time that I was perf lead, and so it was basically under my leadership, which was funny. Back then it seemed to be like great thing, and we improved things from performance reason, and didn't realize that the buffer lifetime management is not quite right. What we were then digging into was interesting to find out, like, so why was this triggered? Like, what happened? Like, why suddenly, since 4.5.2 until now, which was 4.7.1, whatever version, nobody it wasn't triggered. And luckily, we had Skype team who was amazing. They basically had ability to take our private builds, put them to production. They didn't care too much if it is a little bit broken because they had like retries and things, and they said like, yeah, whatever. Like if you go from 1% failure to 10%, we're good. It was like, I love it. Like when you have this type of like how is it like I don't test, and when I do it in production. So yeah, this was exactly that. So we loved it because like when you have this complicated repro and like this type of thing, how do you how are you sure even if you track it down on your repro that that's the real thing in production? And it was already the second bug, right? We already fixed one and we discovered another one. So anyway, with their kind of help, we figured out that actually it was changed in 4.7.1 that triggered it. What was mind-blowing is, first of all, the change that triggered this problem was actually partial fix of this bug. So there was something basically, imagine that you start, in method you start, and we go went down and hold on the buffer. And the change in 4.7.1 was that we moved oh, you know what, let's release the buffer here. The right change that we did actually with this was, oh, release it even higher. So you could view it that like, oh, we kind of created the window when the buffer could be reused was like smaller. Go figure. It was smaller, yet suddenly it triggered somehow the issue. Fun times. And so to make it even more interesting, through code reviews, we couldn't hit this in the repro. We actually found out we have similar type of bug of lifetime management not on the sending side, but on the receiving side. And that was introduced the same at the same time. It was entirely different code, different principle, but the lifetime was just not right. So that was fun thing because basically you find out that you suddenly out of the blue you hit 2 issues, probably 3, which have same symptoms and they are kind of independent at the same time. So first question we ask, like hey, why so many customers or services? And actually we counted what we did. Actually we then talked with a bunch of a bunch of teams in Microsoft and asked them like, did you hit it? Did you hit this? And they went through their logs, and most of them like, yeah, you know what? That's the 0.01% of our failure rate could be this, because of that certain signature, I forgot what it was, like 404 or something. But it was under the threshold that they care about. And suddenly, out of the blue, multiple services were hit by this hard. The best thing that honestly we came up with, that it was kind of after the Spectra meltdown, which had some kind of impact on performance fixes in OS, and that's the best thing that we can kind of imagine. We even tried, afterwards, various things, how it triggers, doesn't trigger, why this, and we couldn't come up with anything. So either that or basically just magic. I started believing in magic. So lesson learned from this is like weird coincidences can happen. 3 bugs at the same time, or 2 to 3. I don't know. I still cannot process that fully. Anyway, that's roughly about it. So I'm going to wrap it up, and I want to kind of review the lessons that we learned today. Hopefully, the key takeaways that you guys can have, folks. So first of all, we went for the always ask, or at least from our side, or don't be surprised when we do, does it repro only on one machine? And if you think that we're just stalling, we're not. We're protecting ourselves from the extremely expensive investigation and costly. And yeah, it's at the cost that you have to try it on another machine when you hit a bug, but at the end of the day, life is better. Because debugging hardware issues, if it comes to that, is extremely costly. Some bugs happen only once per 17 years. Should we fix them or not? That's a good question. Spec bugs are extremely hard to fix because the impact in the metadata format, if you saw across the ecosystem, would be a nightmare. Luckily, it was the once in 17 years, so we could kind of downplay it, but imagine it would be more often. And if it's rolled out spec, suddenly it becomes problematic. Other thing, really anything, has risk of breaking someone. So that was the story about the latent bug or the 8 kilobytes things that, in something entirely unrelated can trigger bugs. So just be careful about that, or be prepared for fun times. And sometimes the impact can be really huge. It was the tax season thingy. And one thing, actually, if you can come up with this from this talk with one learning, I would ask you, always try to create small repros. By the way, if you ever saw me on GitHub on CoreFX, that's the first answer you're gonna get from me. Do you have a small repro? Give me minimal repro. Oftentimes people say but I don't have time for that. I was like, do I have time to debug your whole application? No, try to create small repro. Obviously, it's not always possible, but you see that one of the stories was actually the networking. The people were able to get small repro. It's just, so much easier to debug. Without the small repro, I think it would take us probably 2 months. Hands-on, again, something that we could pull off in less than a week, right? So having small repro, not having, is very huge, change. And you're gonna make your life easier. You're gonna make everyone's life easier. Even though it's some investment, it costs something, but it's just worth it. Other thing, if you can look up the TTD, time travel debugging, I highly recommend that. If you run into some of these cool, crazy things, it might save. It's a lifesaver, or time saver as well, obviously. And the key takeaway is, I think that sometimes there's just magic. There's no explanation why things happen like that. And at certain point, as engineers, we want to understand everything, obviously. But sometimes it's like, you know what? I tried hard enough. I give up. It's fixed, or whatever we have worked around. Let's move on, right? Thank you very much. I would like to ask you for feedback after this. I don't know why I made it this way. Sorry. Now you see everything. Hopefully you enjoyed the talk. If you have feedback, hit me on DM, on Twitter, email, or over here in person. I would love to hear, what you liked, what you didn't like. Was it too rushed? Actually, I ended up 10 minutes beforehand, which is awesome. I didn't expect that. If something was hard to understand, boring, or whatnot, I love feedback. That helps me. And as you see in the tweet, which I did actually yesterday, there are more, apply this to other speakers as well. Speakers love feedback because that's the only way how we can get better. So thank you very much.